Hello, discrete math fans. We're going to discuss the specifics of how computers represent integers. Now bear in mind that we're going to limit all of our examples to 8-bit calculations. That's just to make our life easy. All the principles of what we're working on will remain the same if you used a larger word size, like 32 bits or 64 bits. Conceptually, everything remains the same. Let's suppose we have an integer that's between 1 and 128. Now let's take this inequality and multiply everything by -1. Remember that when you multiply an inequality by a negative number, you switch the direction of the inequality. So we have these are less than or equal to, but they turn into greater than or equal to. And if we take this inequality and add 2 to the 8th to everything, we get this inequality. Now let's take a look at this number on the end here, 2 to the 8th minus 128. 2 to the 8th minus 128 is 256 minus 128. That's 128, which is 2 to the 7th. So remember that the thing on the inside of the inequality, which was 2 to the 8th minus n, that's the 2's complement of n. And so what we've proven is that the 2's complement of n lies between 2 to the 7th and 2 to the 8th, with a strict inequality on this side. That means the 2's complement of an integer that's between 1 and 128 has a leading bit of 1. Think about what happens when you have a number that's between 2 to the 7th and 2 to the 8th, not including 2 to the 8th. It's going to have a leading bit of 1, and it'll be an 8-bit number. Notice also that the ordinary 8-bit representation of a number between 1 and 127 has a leading bit of 0. So we can actually use 8 bits to represent both negative integers and positive integers. Here's how we'll do it. We're going to use ordinary 8-bit binary notation for non-negative integers up to 127. So that's 0 up to 127. For negative integers between -1 and -128, we're going to use the 2's complement of the absolute value of the number. So just as an example, let's find 8-bit representations of 43 and -28. Now 43 is easy. We just follow the ordinary method of doing things. We write it in binary by finding powers of 2 that add up to 43. So for 28, we're first going to find the representation of 28, and that's going to be 000111100. Okay, so you should convince yourself that 28 can be written this way, and then the next thing we do is we find the 2's complement. Remember how we do this? We take our result, which is this guy, we flip the bits, and then we add 1. And so what you see here should be our final result as the representation of -28. Okay, that's all for now.